Believe. Oh, no. Try it again.
That's fine. Actually, talk. That's not how I'm. Sorry. You recognize? So. We're gonna get. I think. I think. I know you. Oh, I have exam. I think.
Okay. Uh, that was an example of a Rube Goldberg machine where you try to accomplish a simple task in as complicated a manner as possible. And what you saw there were a lot of different energy transfers from one form of energy to another. There's a little blurb that goes along with that. There are no computer graphics or digital tricks in these images. Everything that you see happened in real time exactly as you see it. The recording required 606 takes, and in the first 605 takes, there always was something, usually of minor importance, that didn't work. It was necessary for the recording team to install the setup time after time, and it took several weeks working night and day to achieve this effect. The recording cost $6 million and took 3 months to finish, including the engineering design of the sequence. There were only 6 Honda Accords built by hand in the whole world. And to the horror of Honda engineers, the recording team disassembled 2 of them for the recording. Everything you see in the sequence, beside the walls, floor, ramp, and the untouched Honda Accord, is part of those 2 automobiles. The voice is that of Garrison Keillor. That's probably where most of the $6 million went. The commercial was so well received by Honda execs when they saw it that their first comment was how amazing the computer graphics were. They almost fell out of their chairs when told that the recording was real without any graphics manipulation. I really like that because my wife and I, we originally owned 2 of those cars, not the ones that they hand built, but 2 of them. And now we only have 1, but it has a lot of parts from the other one. So, you know, 1994 is a very good year. Okay, let's talk about the different kinds of energy. But before we do, let's have a prayer. Would someone be willing? Would you please?
Heavenly Father, we thank you for this day. We thank you for this opportunity we have to be here together to be able to
learn about physics and to be able to learn about how laws govern the world. And we're grateful for all the blessings that has given us. Our beloved Son, we ask you to please bless us to go forward, be able to learn more. And for those who have not done the test, do well on the test. And please bless the Spirit to be with us and make these things that we just
Thank you. So I don't want to get your hopes up. We're not going to do the bed of death today. We are going to do it Thursday. Okay, I'm going to lie on the bed of death. We're going to put a chest plate of death with nails on my chest. The cinder block of death will go on the chest plate of death, and then the assistant of death. It might be Sam. It might be one of you. Oh, volunteer right over here. Have you, sir, taken the exam, and how did you do? Not yet. Okay. Let's see. We'll see. Okay. Someone that did well on the second exam. The assistant of death will sling the sledgehammer of death. Cutler brought this over, and that's not the sledgehammer of death. The sledgehammer of death is this tall and big old honking thing. He's new. Okay. Anyway, death all around, and if I live, we'll talk about momentum. But not till Thursday. Not till Thursday. So let's review where we've been. We ended up last day kind of in a rush, talking about what changed kinetic energy. And we found that what changed kinetic energy was the Werk. Work is what it's usually called, but we want to set it apart from what you do on the ranch. And so we call it Werk. It's force times the distance, but you have to worry about some subtleties. It turns out that if you're pushing in the same direction as the motion, that's positive Werk, and it increases the kinetic energy. We would say that the change in kinetic energy is a positive number. If you push opposite the motion, that slows things down. You're taking energy out of the system, and you're doing negative Werk. And so we would say the change in kinetic energy is a negative number. This is where things get strange. If as you're going to the right, someone were to pull on you straight up, always perpendicular to your motion, we find that that doesn't change the kinetic energy. You don't slow down, you don't speed up. And so we would say that that is zero Werk. And that's what makes it different from work that you would do on the ranch. Now, because of that complication, our definition of work is a little bit messy. It can be a positive force times the distance if they're in the same direction. And it doesn't matter what direction that is, left, right, up, down, up and to the right, as long as it's the same. It's negative force times the distance if those are in opposite directions, and it's zero if those are perpendicular to each other. And that's the definition that you're going to need as you work your problem. Now, I mentioned when we started talking about energy, I gave you good news that energy is a scalar, not a vector. We don't have to worry about vectors. Yay! Well, I was exaggerating, okay? Because when you're worried about the work done, the Werk done, you have to figure out which of those categories your force falls in. And sometimes it doesn't fall into one category all by its onesie. For example, if I were pulling on this rope at 1,000 newtons at an arbitrary angle, let's call it 37 degrees, and I wanted to know how much Werk was done, what would be the first question you would ask me? Brave soul. Has to be something you're curious about. Yes, sir.
How far does it go?
Yeah, how far did I pull? You know, if I pulled for 5 meters, how much Werk was done? And then the question is that 1,000 newtons doing positive Werk, negative Werk, or zero Werk? Well, because that 1,000 newtons isn't in the same direction and it's not perpendicular, I have to break it up into parts, components. And so that red component that's parallel to the motion would be doing positive Werk. And the amount of Werk that it is doing, this one, okay, is just the force times the distance, or 4,000 joules. This blue component here is just like pulling up on my hair as I go scooting by on the skateboard. It does no Werk whatsoever. So we're still going to need to do a little bit of vector work, a little bit of trigonometry as we do these problems.
Would you use the net force for the force that you're multiplying by the change in distance, or just like if there was like a friction?
In this case, I was only worried about the work done by that tension force. And so if there was a friction force, I could ask a second question, how much work was done by the friction force? That would be a negative number. Okay, last day, in order to get you ready for the tutorial, we had to quickly talk about Hooke's law. And you remember it was fairly simple. It was just that the force exerted by a spring is proportional. There's the force, there's the spring constant, the proportionality to the stretch or compression of the spring. This delta S is how different the spring length is from when it came out of the box from the factory. Okay, how different the spring is from how long it wants to be. Okay, and what we found is that minus sign is just a waste of our time. We have so many minus signs in this introductory class, and they trip us up over and over again. They mean different things in different situations. This is one that we can just ignore, because that's all it's saying is that if I pull down on the spring, it pulls up. Okay, my displacement and my force by the spring are in opposite directions. So we're just gonna ignore that minus sign for the rest of the semester. Now, that force constant tells me how stiff the spring is. If I take a little tiny spring off of a sewing machine, it's really easy to stretch it. And so it would have a very small spring constant. If I go back, when you have this definition and you want to know what the spring constant means, plug in 1 for delta S. And if delta S is 1, then the spring constant is how much force you have to pull with in order to stretch or compress a spring by 1 unit of length, by 1 meter. Okay. Now, a lot of springs you've seen, if you stretch it by 1 meter, you bought it, you broke it. It's just not the same as it used to be. So you can also see how hard it is to stretch it by 10 centimeters and multiply that by 10 if you need to. Okay. The larger the K value, the stiffer the spring, and the units are newtons. Let's pronounce this for each meter of stretch. How many newtons of force it would take to change the length of that spring by 1 meter? Check with your neighbor real quick. Make sure they understand spring constant.
Shout out 116 Strawberry Dream.
You good?
I don't. I like
This is just an aside. there are 665 students in the class. It turns out that 83 of you took the exam on either Friday or Saturday. So a lot of you chose to wait over the weekend there. I graded all 83 of those exams by my onesie yesterday, and they did amazing. They did amazing. So I would suggest that in the future you take your exam on Friday or Saturday, because those tests turn out really good. Okay. We introduced this new bucket, spring potential energy. And you remember, energy is the capacity to do damage. And a spring that is stretched or compressed, if it's a big enough spring, you should be afraid of it. Okay, it has the capacity to put a hole in you. Now, where did this formula come from? I gave it to you. I asked you to trust me. Well, that ends today. Okay, today I'm going to show you where these formulas come from. But first, let's look at this example. We've got a 10-kilogram block, and it's pushed up against this spring. It's not connected, it's just pushed up, and it compresses the spring by 0.5 meters. And so if the spring constant is 16,000 newtons for each meter, that hand has to be a very impressive person. Okay, that is a strong individual, but they compress that by 0.5 meter. Now, we see that it's not moving, the block's not moving, so there's nothing in the kinetic energy bucket. If we define this floor to be our height 0, there's nothing in the potential energy gravitational bucket. Now, what do these hash marks mean? Well, I use those, that's my notation for friction, that this is a rough piece of ground where the coefficient of kinetic friction is 0.2. And if I don't have the hash marks, that's a frictionless surface, no friction, okay? Very slippery. Now, I do have potential energy stored in the spring, and if I use the formula for that, 1/2 times K times the compression squared. And folks, another aside, the most common mistake on the next exam will be not squaring that. Okay. Oh, you'll write it. You just won't do it in your calculator. Okay. Turn to your neighbor and say, that'll be you, not me.
Yeah.
Look, changing again.
Okay. That's going to give me 2,000 joules. And you remember that this total energy bucket is just the sum of all the individual buckets. And so it's going to have 2,000 joules in it. Now, if I were to release that block, and no, it's not my hand, okay, if the strong person releases the block, and we want to know after it gets away from the spring, how much kinetic energy does it have over there? Well, when I ask this question on exams, I find a lot of people do it the hard way. They go through a whole lot of trouble to find out how fast that block is going, and then they plug into 1/2 mv squared, because that's what kinetic energy is. That's what Greg told us, 1/2 mv squared. And so they go through all sorts of rigmarole to find out how fast it's going. Well, let me show you a better way. I had 2,000 joules, total energy. I didn't get robbed. This is a frictionless surface. There was nothing doing Werk on that thing. The only thing that's acting on that block is weight pulling down, but that's perpendicular to the motion. The normal force pushing up, that's perpendicular to the motion. There's no Werk being done on this system. And so that means I didn't get robbed. I still have the 2000 joules. But where is it? It's not in the spring anymore. It's in the kinetic energy bucket. And so the answer is I had 2000, I still got 2000, 2000. Okay. If you walk through Central Park and you don't get mugged, you still got as much money as you started with. That's that easy. Okay. Now, once I know there's 2000 joules of kinetic energy, now I can work backwards to find the speed of that block. I just say that 2000 joules is equal to 1/2 the mass times the speed squared. And if I solve for that speed, I get 20 meters per second. So that's the way to find the speed, the easy way. Okay. Now, if I tried to find the speed using the kinematic equations, would I have gotten anywhere? And the answer is no. Not when there's a spring involved, because the spring pushes harder when it's compressed more. And so as that spring is being relaxed, the push by the spring changes. It gets smaller and smaller. And that means the acceleration of that block while the spring is pushing it is not a constant number, which means we can't use those kinematic equations. Okay, now how far will that block slide past point B before it comes to a stop? Well, that is an important question that we will see over and over and over again before this next midterm. Now, let me show you how to find that the easy way. Let's go back to our equation that we started with when we were introducing the idea of Werk. The Werk changes the kinetic energy. And I'm just going to do a little algebra here, but nobody's going to get harmed. Nobody will be hurt, okay? It won't take us long. I've got kinetic energy final minus the kinetic energy initial. If I take that kinetic energy initial and put it over here, it becomes positive. Now, if I take the left side and trade it with the right side, it looks like that. And I would read this as the kinetic energy in the morning is always, always, always equal to the kinetic energy at night, except when it isn't. And it usually isn't. It isn't whenever something does Werk on it. Okay? Now, in this problem that we were doing, there was only one bucket. There were no springs. Everything happened on a level floor that we called height 0. So the only bucket we had was kinetic. Well, what about a more general problem where I've got springs and I've got hills? What would this look like? Well, it would look like this. Instead of kinetic energy, I would have total energy. And the total energy in the morning would always be the total energy at night, except when it isn't. And it isn't when something does Werk on it. Now, there's another way to change total energy, and that's to put a flame under it, to heat it. But we're going to let the chemistry department deal with that. We're not going to worry about that in this class, okay? No open flames, okay? Now, I want you to take a good look at that equation. It's called the Werk-Energy equation, and it's the starting point for every energy problem. In your homework, on the exams and the tutorials, if you have an energy problem, you start with this equation there. And then you ask yourself, what do I mean by the initial event? And what do I mean by the final event? And you get to choose. And you should choose one of those to be a time when you know everything about the energy, and the other one to be a time when you're looking for information. And whichever one happened earlier in the day will be the initial, and the other one will be the final. Okay? And then at each of those events, you ask yourself the same 3 questions, always the same 3 questions. at this initial time, was anything with mass moving? If so, I've got kinetic energy. Second question, is anything up off the floor? If so, I have gravitational energy. Third question, are any springs stretched or compressed? If so, I have spring energy. And then I go to the final event and I ask the same three questions. Now, once you do that and you put in those energies that are present, what you're going to find is algebra. You're going to find that you've just got a whole bunch of variables that you have numbers for and one that you don't. And then you just solve for that one unknown. Okay? So let's do that with this problem. Remember, we want to know how far is this block going to slide before it stops if its coefficient of kinetic friction is 0.2. Well, I started with 2,000 joules. I end up with no joules. I get robbed. So this Werk must be how big? Negative 2,000 joules. So if I go back and work this, all I need to know is the friction force. Maybe I need to slow down and do that. You have to remember, I'm used to a room where I have a whiteboard and okay, so I had energy initial plus Werk is equal to energy final. When the bucket was full, I had 2,000 joules. And then the friction force did negative Werk because it was moving to the right while the friction was pushing to the left. And it's kinetic friction. I can hear the scraping going on by the table on the block times how far it slides. And that gets me down to 0 energy. So if I know the friction force, I can find the distance that it slides. I've known how to find that friction force for quite some time. I draw a free body diagram. The weight force of that 10 kilogram block is going to be 100 newtons. The normal force by the table on the block would also be 100 newtons. There's no acceleration up or down. The friction force is the easy kind of friction. mu sub k times the normal force. That's 0.2 times 100, and that's going to give me 20 newtons. So I go up here and I plug in 20 newtons, and I solve for delta x, and that gives me 100 meters. Now, folks, that gives you some information about coefficients of kinetic friction. If I have a coefficient of 0.2, this thing that starts out going 20 meters per second, 40 miles an hour, is going to slide a whole football field before stopping. Okay? Is 0.2 a slippery road or a rough road? Tell your neighbor.
Slippery.
So I think I told you before that I went to high school on Guam, and in the early morning, I was responsible for picking up all of the seminary kids in my part of the island crammed into a little VW bus. And in Guam, it's just sunny every day, but it rains every night. And when you wake up early in the morning, all of the roads are covered with snails. But these aren't little snails. These are great big old snails that are just all over the road. So you're going crunch, 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 crunch. And turns out that when you hit the brakes on those roads with those snail guts, you just keep on going. And so the maximum speed limit on the island was 25 miles an hour, but not for my brothers. My brothers have different rules. Okay. Now it's time for me to show you where those formulas come from. And I'm going to do it with a special little trick. And that is, I'm going to fill the total energy bucket in a special way that the energy only goes into one of the individual buckets. Let me show you what I mean. If I start with this block that's already moving at some slow velocity, and I lift it a distance h in such a way that that velocity never changes. It started out slow, it was always slow, and it ends up slow up there. Well, if I look at the buckets, initially, since it's moving, I've got something in the kinetic energy bucket. But if I call this height 0, the lowest point in the problem, I have nothing in my gravitational bucket. And there's no springs in this problem, so there's nothing in this bucket. So the total energy is just what I had in that kinetic energy bucket. Now, if I look up there, well, I still have the same amount in the kinetic energy bucket. It's still going the same speed. But now I have something in my gravitational bucket. I still don't have anything in my spring bucket. There's no springs. And so my total energy bucket has filled. Okay. I have filled this total energy bucket in such a way that only one bucket changed, the gravitational bucket. This one stayed the same, and this one stayed the same. Now, if I'm filling the total energy bucket, I must have done it by doing positive Werk. That's what changes total energy. Well, let's calculate that Werk that the hand had to do. Well, the Werk is just going to be a force times the distance. And because the hand is pushing in the same direction it's going, it's going to be a positive Werk. Well, the question is, how hard does that hand have to push to make this go at constant speed? And I hope you all say the weight. Okay, if I draw a free body diagram for that block, I got weight down, which is mg, and I got the hand pushing up. But if the hand's pushing at constant velocity, 0 acceleration, that diagram has to screen balance. Okay, and so this is the force, mg, and this is the distance, h. Well, that looks familiar, mgh. Well, that's my formula for filling the gravitational potential energy bucket. Just how much Werk I had to do to get that block up there. See if your neighbor followed that reasoning. See if your neighbor understood that.
Oh, so because of he's saying that. Describing always been the same.
Okay. Now, if I had given you that derivation last week, it would have just been math. But now I hope that it just makes sense. Oh, just how much Werk it needs to fill that one bucket. Well, let's do this again, but now with springs. Okay, and in this case, what I have is a spring. I'm going to walk right past you, my friend. And this spring, when it came from the factory, was this long from here to here. So when the spring is here, it's not stretched or compressed. That's just how long the spring wants to be. And then the hand is going to push the spring, push the block, and the block's going to compress the spring to here. Now, this is important. This time we're going to start from rest. Nothing's moving. We're going to move it at a slow, constant velocity. And then we're going to stop again. So it goes from rest to rest. Okay. Now, if we look at the buckets again, if I look here, this is my starting place. Nothing's moving. Everything's on this floor that we're going to call height 0. So there's nothing in this bucket. The spring is not compressed yet. So there's nothing in that bucket. So there's no total energy. Well, now let's go over here. I stopped here, so there's nothing in the kinetic energy bucket. I'm still on the floor, so there's nothing here. But now the spring has energy in it, the capacity to do damage. So I just changed the total energy from nothing to something. Well, that takes Werk, positive Werk. And so in order to go from no energy to some energy, I had to do positive Werk. And all I have to do is calculate how much Werk I had to do to get from here to here. And that'll be my formula for filling up that bucket. So let's do that, okay? I know that the Werk is the force times the distance. I know that the distance is delta S. That's the compression of the spring. And I know from Hooke's law that the force by a spring that I'm fighting will be K delta S. And so if I multiply those together, I get K delta S squared. Looks familiar, doesn't it? That's the energy stored in a spring. Bada bing, bada boom. How we doing? Everyone comfortable with that? Yes, sir.
It's 1/2 K.
Oh, you thought it was 1/2. Okay, so you're gonna quibble over a 1/2. Yeah, I'm half right. Is that what you're saying? Yes, half right. Okay. Let's talk about that half. That half is incredibly important. That half is the difference between you doing calculus and not doing calculus. Okay, let's talk about it. The force by the spring is K delta S. But only here when the spring is already compressed by delta S. If I look over here, the spring is not pushing at all. And so I don't have to push at all. So think about me compressing this spring with the block. At first, I don't have to hardly push. It's so easy, so easy. And then as the spring gets compressed, it gets harder and harder and harder. This hard, okay? Now, some mathematicians would say, well, you have to use calculus to figure out all the work that you did from here to here because it changes as you go. But we know in our guts that we don't need to do calculus. If you're doing calculus, you're just not doing it clever enough, okay? So what we're going to do is we're not going to use the maximum force. We're not going to use the minimum force. We're going to use the average force. And the average force is halfway in between. Okay, that half gets us away from doing calculus. And so now when we calculate the Werk, it's just the average force while we're compressing it times the total compression. And that's where we get that 1/2, which is in the formula for filling up the spring potential energy bucket. See if your neighbor's on the bus, people. No child left behind. Yeah. I don't know. When, yeah, so As delta S gets bigger and bigger, that force gets bigger and bigger. And so the delta F that I've got is the maximum delta F. So that would be the maximum force.
Really?
Good. Yeah. Wouldn't be hard.
No.
Yeah. Okay. I feel so much better now. You don't have to trust me. I don't have to feel guilty for not teaching you how this came about. Everything's good. Okay, you've all been to the lagoon, you've been on this ride, and you know what a loop-de-loop is. Well, if I had a track that was a loop-de-loop and it were completely frictionless, imagine if you will, a totally frictionless loop-de-loop, and I send a marble going around that thing, would its mechanical energy increase, decrease, or stay the same? We're going to use our clickers. And folks, I'm sorry, this should be A, B, and C, but that's not a big stretch. Okay. Okay, now you can click.
Oh, it's got an increase. All right, put it. Potential higher. Good.
Okay, last call, get your vote in. Okay, stays the same as the correct answer. Now, why? Well, remember our definition of Werk, and remember it's Werk that changes energy. In a frictionless track, the track only exerts one kind of force on your object, namely the normal force. But the normal force, by definition, is always perpendicular to the track. No matter how convoluted that track is, the normal force will always be perpendicular to us. The marble has to move along the track or parallel to the track. That means that the motion and the force are always perpendicular to each other. So a frictionless track will never do any Werk on what's sliding on that frictionless track. Now that allows us to make some exam questions, some tutorial questions, some homework questions that really look messy. We can have all sorts of carnival rides with convoluted tracks, loop-de-loops, and it looks challenging, it looks terrifying, but it's not. If it's frictionless, doesn't change the energy. And we'll see enough examples that you will feel comfortable with that by the time you get to the next exam. Now, I have an old exam question, actually two of them, but we're only going to look at one today. Okay, I need help. Who's going to help me? Thank you for helping me. You're always so helpful. Thank you. Okay. We're going to look at the problem that has the same picture on the slide. We're going to have to get them from the other side here. Okay, leftovers. Loaves and fishes.
That's my favorite thing about the strips.
I'll take those back. Who still needs one? Okay.
They actually don't care. I was like.
You got it already. More?
Yeah.
Okay. What we have here is a block that starts from rest at A, slides down this frictionless track, and then it encounters this rough patch with a coefficient of kinetic friction of 0.3, and the patch is 2 meters long. And then it bounces into a spring where it turns around and goes the other way. And so it momentarily stops. It has to stop to turn around. And so we're going to work this together. So the first question, when it was on an exam, was only worth 2 points. And it was find the work. See, we misspelled it. Could be Werk. If any, those are the most important words in that sentence, done by the ramp on the system as the block moves from A to B. And remember, there's no friction from A to B. So the answer to that is 0. And the reasoning is the normal force by the track is always perpendicular to the motion, so it does no Werk. So B is where I encountered an uprising in my class in Montana. In B, I asked for the kinetic energy at point B. And on my solution key, yes. Oh, it's speeding up, but there's no friction. Yep. Oh, yeah, there is. No, the potential energy is changing, the kinetic energy is changing. It's the total energy that's not changing, which is the sum. And so what we're doing is we're sloshing potential energy into the kinetic energy bucket. I'll show you, okay? What I put on my key was that the kinetic energy at B was equal to the mass times G times the height at A. And the students were so mad, they said, Greg, you lying sack of spit. You told us that kinetic energy was 1/2 mv squared. You told us to trust you. We trusted you. And then all of a sudden it's MGH. Okay. What I did is I left out a step. What I should have said was that energy initial plus Werk is equal to energy final. And I'm going to take the initial to be at point A, and I'm going to take the final to be point B. And that's because I know everything about the energy here, and I want to know something about the energy there. Because it's frictionless, there would be no Werk. So then I go to the 2 events, A and B, and I ask the same 3 questions. Is anything with mass moving at A? Not yet. Is anything up off the floor? Yes. So I have potential energy gravitational at A. Are any spring stretched or compressed? Not yet, not at A. Then I go here and I ask the same question. Is anything with mass moving? Yes. So I have kinetic energy. Is anything up off the floor? No. Any spring stretched or compressed? No. So that means that the kinetic energy at B, which I'm looking for, is the same as the gravitational potential energy at A. And I know what this is. That's just M times G times the height at A. Does that make sense? And so if I look up there, MGH gives me 80 joules. 10 times 10 times 0.8 gives me 80 joules. And since I wasn't robbed, I still have 80 joules when I get down there. Okay, then we go to part C, and we're looking for the magnitude of the friction force. Well, we've known how to do this for quite some time. I have a weight force of the block that's 100 newtons. I have a normal force by the track on the block that's 100 newtons. I have a friction force, it's the easy kind of friction. That's just mu sub k times the normal by the track on the block. These indices will always be the same. And so that's going to be 0.3 times 100 newtons or 30 newtons. And then I need to find the kinetic energy at point C. Well, if I go to my energy Werk equation, I'm looking for the energy at C, so that should be one of my points. Whether I choose my initial point to be A or B, it doesn't matter, because it's going to be 80 joules either way. So I'm going to just call that B, and then I have 80 joules, and then I have negative work done by the friction force times the distance of 2 meters. Well, the friction force, let's just write it out. The friction force was 30 newtons, and the distance was 2 meters. And at C, the only bucket that has energy in it is the kinetic energy bucket. So one way of thinking of this is I started that rough patch with 80 joules. The rough patch robbed me by 60. The work done was negative 60 joules. And so I've got 20 joules left. Okay. How are we doing so far? Making sense? Okay.
Friction,
Now we go to part E.
30 newtons.
Oh, question. Where?
It's right here.
There you.
I'm just wondering why the work is the friction force times the distance. Like, where did that go?
Why is this negative?
No, just the 30 newtons times 2 meters. Why is the work equal to that?
Oh, remember our definition of Werk is always force times distance. And if they're in the same direction, it's a positive force times distance. If they're in opposite directions, it's a negative force times distance. And that's what we've got here. The friction force is doing the Werk. It's pointing this way while the block is moving that way. So it's just a definition of Werk. Okay. Now in part E, again, I'm going to use my energy equation. And in this problem, I want to know how compresses the spring when the block stops moving to turn around. And so I want my final here to be the turnaround point. And my initial, I'm going to choose to be point C so that I don't have to look at any Werk there. Because between C and the turnaround point, I'm back in this frictionless track. There's no robbing going on. And so this is going to be 20 joules plus 0. At the turnaround point, nothing's moving, so I don't have kinetic energy. Nothing's off the floor, so I don't have gravitational energy, but I do have a compressed spring, 1/2 times K times delta S squared. Question?
Question is, it talks about how we're considering the block group spring system.
Yes,
Um,
I will in just a moment if you give me 5 minutes. Okay. So let's solve for delta S. If I multiply both sides by 2, this becomes 40. If I divide by 160, this becomes a fourth, is equal to delta S squared. And that gives me a delta S of 1/2 meter. See how easy these energy problems become? They very quickly just become algebra, and then we just solve for the unknown. Check on your neighbor real quick.
I'm gonna get this.
I'm a big fan of
Get this one. You're gonna go for the ones. Which is what happened. Yeah. Well, thank you.
Okay.
that equals the kinetic energy.
The exam on the back of that, or the question on the back of that page is straight off of the midterm for spring term that I just finished teaching before this semester. And so that's representative of what type of question you can expect on your next midterm. Yeah, okay?
Joke's on you.
Okay. We can also dance these problems backwards. I could have written the problem this way. A block of mass 10 kilograms slides from rest on a frictionless ramp such that the center of the block drops the distance 8. As the block passes from B to C, it encounters a 2-meter stretch of track that is rough, having a coefficient of kinetic friction of 0.3. After passing point C, the block compresses a spring by an amount 0.5 meters and comes to a momentary stop. Find H. So again, you just set up your energy equation, energy initial plus Werk equals energy final. And this time, you'd work backwards and you'd find out what H had to be, that it had to be 0.8 meters. You can dance forward or backwards, unless you're a guy. Okay, this is one of your homework problems, and it was put on an exam in 1998. My friend Jeff Adams and I were teaching together, and we put this question on the exam as question number 1, thinking that everyone would get it quickly right, and it would build their confidence and send them through the rest of the exam with warmth in their hearts. What we found instead was that our students were spending 45 minutes on it and getting it wrong. Okay, so let's talk about this. Tarzan swings on a rope from a ledge that's 5 meters above the lake. The rope is fastened to a tree limb that is 6 meters above the lake's surface. When Tarzan lets go, he has risen to a height of 2 meters above the water. How fast is Tarzan traveling just before he hits the water? Now, energy is conserved in this problem, true or false? I'm gonna get you started, just a second. Now you can click.
I feel like the answer's probably.
If we hit the water.
They're like swings, since there's something in land. Rob's this.
Either.
Yeah.
Freeze the water.
Yeah, why?
Okay. This is not rocket science. Rocket science is Thursday.
I feel like
We're almost there. You will be rocket scientist. Yeah. Okay, are we done? We're done. Okay. Good. The answer is true, provided that we ignore air resistance. Well, why doesn't that Tarzan rope do there? Well, if we think about that Tarzan rope, it's always pulling along the rope. That's what ropes do. And Tarzan is always moving perpendicular to the rope. That's what Tarzans do. And so the motion and the pull are always perpendicular to each other, just like on a frictionless track. So energy is conserved. So let's use our energy buckets. When he's standing there getting ready to swing, all the energy is in the gravitational bucket. Nothing's in the kinetic energy bucket. When he lets go of the rope, he still has the same amount of total energy, but some of it is now in the kinetic energy bucket. He's moving, and not as much as in the gravitational bucket. But right before he hits the water, don't let him hit the water. Right before he hits the water, he still has all of the energy. It was conserved. It stayed the same. But if we call that height 0 there, all of the energy is going to be in that kinetic energy bucket. So why did my students get this wrong, and why did it take them 45 minutes? Because I gave them that piece of information, and they thought they needed to use it. They used energy to figure out how fast he was going here. They used some awful trigonometry to figure out what angle he was going. And then they turned it into a messy projectile motion problem and got the wrong answer. Again, let me show you a more excellent way. It turns out with energy, all you care about is the initial state and the final state, and whether there was any work done in between. But you don't care whether Tarzan let go at 2 meters above the water or 3 meters above the water. You don't care whether he does a full gainer or a twist. It don't matter. All that matters is that the initial energy, which is gravitational, is equal to the final energy, which is kinetic. The mass cancels, I solve for V, and I get 10 meters per second. It is that simple. It is indeed that simple. Okay? Now, which person strikes the water with the greater speed, A or B? Both the same. But clearly they are not having the same amount of fun. Okay? The person on the right knows what they're doing. The person on the left has no clue. Probably going to hit a rock. Okay. Okay. Now, let's answer this question, this wonderful question that was asked about system, about when do we put the earth in the system? When do we put this or that in the system? By putting something in a system, we essentially just decide which buckets we can talk about. We have generally a kinetic energy bucket, a gravitational bucket, a spring bucket, and we add those for the total energy. But if I only take the block as my system, if I draw a red circle around the block and only talk about it, what buckets can I talk about? Well, I can talk about the kinetic energy of the block, but can I talk about the spring energy of my system? No, the spring's not in my system. Likewise, if I don't put the earth in my system, I can't put the potential energy in my system. That gravitational potential energy, the capacity to do to do damage because there's a heavy weight over his head. That's not contained in the heavy weight alone. It's the earth pulling on that heavy weight. The fact that they want to get closer together. Without the earth, if we were out in deep space, I would hold an anvil over his head and it'd say, fine, let go. I don't care. Just let go. And it would just hover there. Okay. So if I just call the block my system, I only get one bucket. Okay. Now, watch what happens to the total energy as this time the block is connected to the spring, and watch what happens. I release the block. Originally, it's not moving, and then it gets moving. So I've got energy. And then it's moving really fast. I've got a lot of energy. And then it starts to slow down because the spring is stretching, and then it turns around. And as it goes back and forth, the total energy bucket fills and empties. Now, what's happening? Well, the total energy is filling and emptying because the spring is doing positive and negative work on it. Sometimes it's saying, get away, get away. Other times it's saying, come back, come back. It was kind of like, oh, I shouldn't say this. My daughter during her freshman year at BYU, get away, come back, come back. Anyway, it all worked out great. She's got a wonderful husband. But he was not the first guy that came to our house asking for her hand, I'll tell you. I had one guy sit me down on the floor and start handing me frozen hamburger patties, saying, how many do you want for Heidi? I said, oh, out, so. Okay. It's an old movie, Mahana. You probably get it. Okay. Now, if I include the spring in my system, now I can talk about both the kinetic energy in the block, but I can also talk about the spring energy. And now watch what happens when the block goes back and forth. I start out with a lot of spring energy, a lot of total energy, and then it speeds up, but I don't have as much spring energy, but I keep the total energy. And then I have a lot of kinetic, but the spring is not stretched or compressed. And then the spring starts to stretch, and then all the energy is in the spring. Okay, so watch it as it goes back and forth. That total energy bucket stays the same. And that's something I can work with. That's something I can solve problems with. So you see that that system is a better system to use. So what we're going to have to do is we're going to have to modify our Werk-Energy equation. The truth is ever so subtly different. Did you see that? How? It's only external agents, and this is what you learned in your tutorial. Only external agents that do Werk on a system that can change the energy of the system. Things that are outside of my system. So how do I define my system? Well, the first thing you should always put in your system is anything with mass that moves so that you can talk about kinetic energy. The second thing that you should always put in your system is the earth, by which we mean the gravitational force, so that you can always talk about the gravitational potential energy of the system. What that means is you will never calculate the Werk done by the gravitational force. That's always going to be an internal force. That's part of your system. Instead, you're going to talk about the gravitational potential energy. Third, you're going to include all springs in your system so that you can talk about the spring potential energy of the system. And this is critical if you don't want to do calculus. Because if you leave the spring outside of your system, you've got to calculate the Werk done by the spring. And remember, the push by the spring changes as the spring relaxes. And so you need calculus to do that. But if you put it in your system, you'll never have to calculate the work done by a spring. So what do you put outside of your system? Well, external agents. Oh, no, not them. They're not the external agents. Is that even James Bond to you? Is that even 007 or is it one of these people? Which one?
Yeah.
You're correct.
Okay, that's mine. Okay, I'm on. No. By external agents, we mean like the Tarzan swing or the frictionless ramp. Leave those outside of your system. They do no work, so just leave them out. The lobster hand, or the floor, typically does negative work through friction. Okay, and the lobster hand can do either positive work or negative work, depending on how it's pushing relative to the motion. And bottom line is anything else that's not this, or this. Okay. Now, I was going to end with a story, but I'm thinking that you should get over to your devotional instead. So why don't we end here? And those of you, and I'm talking about 400 of you that haven't taken the exam yet, may the next horse be with you.